Welcome, first of all. I'm pretty impressed by that crowd. Actually, last year was my first time at Troopers, and I was attending Mike Osmond's keynote, where he talked about inventions and patents. And one thing he said was, your thing has no value if you don't show it and if you don't talk about it. So today I'm here to talk a little bit about the thing I built, which is a little bit basics on AI and machine learning. Yeah, maybe a little bit about me first. I'm Matthias Meidinger. I'm a network engineer as well as a computer science master student. And I've got nothing groundbreaking or 0 days today for you, but maybe just spreading a little bit of knowledge that I acquired. Because basically this is part of my master's thesis. So imagine it as a kind of journey of a student learning something about machine learning. So I'll let you in on a thing or two. So the usual disclaimer is, it's not only for the good. There is no affiliation to the employer. But today the disclaimer is it's simplification. There's a lot of math involved. And the spoiler for you is basically no math were heard in the making of this talk. So you don't need to know anything about it. I'm trying to simplify and give you the grip of some basic concepts. So like every great student, I started my research with a thorough review of current trends and tried to just Google IT security and machine learning, and I have to say, it's fear, uncertainty, and doubt. So it's a little bit of marketing lingo going on there. So, I won't tell you which companies I took that from because I'm not nearly getting paid enough to do that. Also, I don't want to ridicule them because imagine being the company, they're not interested in publishing all the technical details and nitty-gritty stuff. They're encapsulating that into a little bit of marketing, which, to be honest, it sounds quite nice compared to the technical details. And yeah, well, of course, I spent way more time looking for these than I probably should have. But let's get on with the basics. They will be a little bit dull, maybe, but I tried to involve some cats and dogs, so at least it will be something entertaining, hopefully. It might get interesting afterwards. So what is all this deep learning talk that you keep on hearing? There are some common terms that I kept finding and tried to look up some explanations for it. So let me give you the shortcut. There's artificial intelligence, which is the complete field or area of science which is defined by a system's ability to correctly interpret data and learn from this data. So this is what artificial intelligence in one of the many definitions is about. There is a specific approach to do machine learning, to do artificial intelligence, and that is machine learning, which is self-driven pattern recognition. So that thing goes ahead and builds mathematical models from training data. So that's all that machine learning is. There is then something special, which is neural networks, which are one specific method of machine learning. So it's basically networks kind of inspired by the neurons in your brain, and the networks are built in layers. And if you stack many of these layers, you get the obvious term of deep learning, which is basically neural networks with many layers. And to give you a feeling where we are today, and how old this stuff is, artificial intelligence was introduced round about here. Don't worry, I will give you some years, but just to start with the relative feeling to get a grip of it. So machine learning was coined shortly afterwards, And the term of neural networks even is older than the research area of artificial intelligence. Then, a long time, nothing happened, and then deep learning happened. So to give you absolute dates, neural networks, it is said that this term was coined by Alan Turing. So we're talking about the 40s and 50s. And then many years, nothing. And somewhere in the 2000s, there was deep learning introduced in the academic community as a term. So what happened? Well, more or less, science had to solve a problem or two, and simply computers weren't strong enough to compute all the different nodes. So that's why we have this big gap that leads to the modern incarnation of deep learning. Yeah, and to start with one of the most important things, I think, let's talk about metrics. So there is, I mean, if you see the marketing, it's nice and fine, but they're not exactly telling you what exactly they are measuring or how you could measure or evaluate such systems. So, I mean, this is a picture of 7 dogs and 4 cats. I mean, I counted probably more than I should have to make absolutely sure there's no error in that. And if I imagine if I say, Alfred, find me all the dogs in that image. And Alfred says, sure, here you go. I found these 3 dogs. So this is your true positive rate, or very well known as the detection rate. So how many correct items did Alfred find? But Alfred doesn't stop there. Alfred tells me, hey, these are dogs too. Well, we as a human know that this isn't true, but he doesn't know. So this is your rate of false alerts or false positive rate, which at least in the terms of, in the context of intrusion detection systems, you try to lower. To give you a feeling, in science for intrusion detection systems, we're talking about true positive rates in the ballpark of 80 to 90% and false positive rates under 10%. That's at least what I found in the papers. So next time you see a salesperson trying to sell you some AI stuff, maybe try asking them if they can tell you any numbers. And I mean, technically I told you there is no math involved, but there's a little bit, just for you, for interest. So the talk is called Alfred, Find the Attacker. So to be honest, I keep talking about Alfred, so let's meet Alfred. This, for the purposes of the talk, is Alfred. A nice little, not perfectly educated golden retriever. And he can, generally speaking, do 2 kinds of things. He can either label things or he can predict numbers. So most systems today are narrow AI or expert systems. They can do one thing, and they can do it very well, even better than a human, but they can only do that one thing. So for the purposes of this talk, imagine Alfred. So labeling means I want to predict a label. So think of, if I give you a bunch of emails, and I would ask you to classify them into 2 piles, spam and ham, the good stuff, oh no, the spam and the good stuff. So if we imagine there are some features like who sent it, how big is it, what does it contain, and we could enter this in a graph, then, I mean, this is kind of easy to differentiate or build some kind of function that tells you, is it on the left or is it on the right? To which class does it, or which class is the mail I'm looking at contained? So this one, quite easy. But unfortunately, reality isn't always that easy. So this one still, yeah, I mean, there's some kind of mathematical function I can build. But if we look at that, that's going to be complicated. So this is the point where we tend to say, OK, well, you know what? Machine, do your thing. So there may be rules, there may be patterns, but we don't see them. The other thing I can do with machine learning besides classification is regression. So trying to predict numerical values, as in, should I pack my jacket to troopers? So I look at the historical data of the last 4 or 5 days before I start, and I try to, well, get an idea or an estimation how the next days could be temperature-wise. Or even another thing you can do with regression is, if I walk the dog every day at 6 a.m., the dog will very soon know when it's 6 a.m. and try to at least wake you up and get you to the walkies. So yeah, this temperature trend is one example of regression. So yeah, but with these tasks, if we think of intrusion detection systems, for example, how do we find outliers? So how do we know that something isn't normal? Well, the idea is something that isn't normal will show up. I can do that with classification, as in I'm trying to build some functions that define the groups. And I can also do that with regression, as in I know the rough estimates where things should be, so if they leave that area, they will most likely be an outlier. So these are the two tasks, but I still need to train my dog. I still need to train or somehow tell Alfred how he should do his job. And I can do this in two ways. I can do this either supervised, so I can present him every item and say, this is spam, this isn't. So the idea of this is you have labeled training data. So you have a pile of emails and every single email is annotated, it's spam or it isn't. And I mean, these training data don't grow on trees, so you have to build them. They are very expensive to create because it almost always involves manual labor, and they're therefore hard to collect. So yeah, it's the idea of teaching your dog a new command, basically. So people thought, okay, supervised is nice, but it's very expensive. There should be unsupervised methods. The idea is you throw your dog in there and just say, go figure something, find groups and find patterns, which means you have unlabeled training data. There is no there is no real truth in the training data, which ends up, this is easy to collect data, but the training is considerably harder and it tends to generate more false positives because it's not that easy to learn on it. Which means this can work out, but sometimes, well, you end up with a dirty dog because you just throw him in there and let him do his thing. So cleanup is to you. So we now have talked about the metrics, the goal, and how to train. But what are we training? Well, there is the ballpark of machine learning and deep learning. So you have everything that is not machine learning, not deep learning, which is linear models or stochastics, basically, and clustering. This stuff is quick in training, so it trains very fast. And there is not that much hardware involved. But on the downside, you have to do feature engineering. So these are mathematical models. So you have to model your data in a way that it works with the algorithm you're trying to feed it to, which can be kind of complicated and error prone. So people tend to say, yeah, okay, isn't there something else I can do? And there is deep learning. That's the hot topic at the moment, a little bit. So this is representation learning. So you're not even trying to, or you don't have to feature engineer because the network tries to learn and make sense of representations in your data. So it tries to do everything for itself. So unsupervised deep learning sounds like a really nice thing because you basically can throw all your data at it and it will just work. Or that's the idea. So on the downside, that one is really hardware intensive. So this is where you need your truckloads of GPUs, your hardware intensive clusters, and you have this weeks or sometimes even months of training time before it can even work. And another downside of using deep learning is mathematical models. A human can understand them. He can look at the equations and kind of trace them back, that's fine. But deep learning, convolutional neural networks and stuff like that, there is even scientists that are doing nothing else than taking completely trained networks and trying to make sense of them and kind of dissect them and looking how or why they say or why they classify things as one or the other. So it's still everything has its ups and downs. So yeah, well, I think that might be enough for the basics. So let's switch on to some practical applications, because I think you're all interested in how in the world can you use this. And again, a small little preface. I'm still not getting paid enough from companies to make to advertise their products. So there won't be any company names in here. And also they tend to protect their technology, so they enclose it in marketing. Yeah, well, also the expert knowledge tends to be not that interesting for customers because they usually just want to have it work and not know how it works. So yeah, this is just some examples, but to get the general gist, I think that's more than enough. And one of the first areas where machine learning saw some usage in the IT security is AV systems and endpoint protection. There's the idea of using regression for that. So you have you get a mail, there's an attachment on it, like a Word document or an image. But for the sake of argument, let's say it's a Word document, and your usual Word documents tend to have something in the ballpark of 1,000 lines of code. And if you start getting mails with 5,000 or 10,000 lines of code, there should be something that's saying, hey, I don't think that's normal, we should have a look at that. You could also do classification. So the more classical tasks of looking at an executable and looking at what does it do if I open it? Does it access some files, or which syscalls is it calling or making use of? Can I classify? There are academic papers that try to classify malware based on their syscalls or basically on their behavior. Another thing, someone told me this morning his credit company called him and exactly this happened. So he lives in the US, he flew over and then started, I think he's collecting whiskey. So the credit card company saw he's living for years and years in the US and buying stuff with his credit card in the US. And then they start seeing stuff happening in Germany, as in he's throwing hundreds of dollars at whiskey in Germany, or at least his card is doing that. So what do? They call him and they say, dude, that doesn't look normal. Are you really sure you're doing that? So you could do regression on the buy history or even the country of origin where you tend to buy stuff. But that's not all you can do with machine learning in this domain. You could also go ahead and do some user behavior analysis. I mean, there are some enterprise CM products that are heavily advertising UBA. What they are doing more often than not is doing regression on, for example, login times. So you have your sysadmin that comes to work Monday to Friday at 8 a.m. And then someone starts logging in with that account on a Sunday night from, I don't know, Germany? Wouldn't be that kind of weird, and maybe it should ring a bell, at least if your company is not based in Germany. So the other idea someone had was profiling user access. So imagine your admin team using the ticket system as well as, I don't know, the conference, for example, whereas your sales team is usually using the CRM as well as accessing some file shares. And when someone, as soon as someone from the sales team starts using the Confluence, I mean, I heard that stuff like that happens, people reading documentation, but I don't know. Maybe we should give the admins a call. So yeah, that's one way to do UBA. But I mean, there has to be something that we can do with code, right? I mean, at least code is somewhat defined. So yeah, we can even look at the applications themselves. So for a classification, I saw some papers of people trying to detect Android malware or profile it, just solely based on the structure of the program, which is kind of impressive. As well as if you think of SQL injections or some common mistakes people tend to make while programming languages are well defined. So there are usually patterns that repeat for common problems. So you could classify or even try to classify stuff like that and find fully automated find SQL injection in your code. I mean, we all dream of it. Would be nice. I don't know if it really works. I was not able to read the paper because of paywalls. So yeah, but you could also go ahead and use or have a look at HTTP communication, which are basically every protocol that you are able to wiretap or look into, or every stateful protocol, I should say. You can use you can try to represent it as numbers, and then try to profile it or try to basically look if there's everything out of the usual, as in the usual is the vast majority of data you have. And finally, we can have a look at the network. So this is my field of work. I'm building or I'm having a look at if machine learning or deep learning is worth the effort compared to classical machine learning terms. Or if it might be a better idea to just stick to easy methods and make use of the real-time capabilities. Because, as I said, deep learning tends to take lots of time and tends to need lots of hardware. So yeah, what can you do? A little bit the same thing as with communication protocols. So you can have a look at the session flags, try to predict the next session flag that will be set for a single TCP session. And if everything else out of the ordinary happens, you can start ringing a bell or closing that device out of or kicking it out of your network if you want to. And as well as trying to classify malicious packets, as in denial of service tends to end with lots of open connections, for example, that are never closed, or with Christmas tree packets, which is always nice to see because these are TCP packets with every single TCP flag set. So you can kind of, there would be no normal application that I am aware of, at least, where you could use such a packet. So if you see such a packet, you're pretty much classifying something as an attack. So yeah, these are the things, or some examples of things that you can do with them. And I keep telling you that you can do them, but how can you do them? I mean, there is a plethora of machine learning frameworks out there, most of them Python. So at least as long as you're trying to do something with machine learning, it might be that you end up learning Python. I'm sorry for that, for anyone who doesn't like Python, but it's the biggest ecosystem I can think of at the moment. So yeah, I've built a test bench because after all, I'm still a student, so I'm lazy. I don't want to do the same things over and over by hand. So I built a Python 3 framework that combines multiple frameworks with multiple data sets. And as I'm currently working at a company that is using Splunk for their stuff, so yeah, I know I'm dropping a name, but that's the only thing I've seen from the only product I was able to have a closer look at. And I threw in some supervised and unsupervised algorithms. So I mean, even Rodrigo in his keynote this morning pointed out that if your experiments aren't reproducible, you're not doing science. So this is what I use to do reproducible tests, and I'm releasing this tool open source, so you can just have a look at it, play around with it. Yeah, how does it work? It's a very small setup. I'm generating data at the moment with 2 separate LANs separated by a firewall. And the firewall is exporting net flows, so network metadata. I don't know what the communication is about, but I know who talks to whom and on which ports do they talk, as well as some TCP session flags if it's TCP, and also or generally the protocol. I know the protocol they are talking on. Yeah, and then I'm using the Splunk SDK to pull data out of the instance and then, yeah, do machine learning with it. So maybe I am lucky to get a working demo today, as the network tends to be sometimes a little bit picky. So let's have a look. I have to say the Splunk instance I'm about to show you was only built for this single purpose. So there's not much data in it. There is I think roughly 15K events in it. So like 30 minutes of testing, which is absolutely not representative for what I'm usually doing, but because of GDPR and stuff, I'm not really able to show you real-world data from my lab. So as you can see, this data obviously really isn't representative. As you can see, the attacker is it's basically a single attack run I captured. So yeah, it's not balanced, it's not nice, it's not well prepared, but it's a demo. And well, I lost my mouse. Let's see. While this is running, what it does is it pulls data exactly this data out of my Splunk instance, or starts to. Yeah, okay. It pulls data out of my instance and then uses that to to feed it to the algorithms. So what I actually did was hide most of the implementation details because I don't think it's too interesting. If you're interested in the nitty-gritty details, come find me after the talk, find me at the shared dinner. I'm more than happy to talk about that. But for the purposes of this demo, let's say you have your time frame, you have to define which data you want to have, and all the data set preparation and bringing it into the right file format happens in the background. This will be refined a little bit to make it a little bit more robust than it is now, because it's built kind of for a single purpose, and I'm trying to build it for all purposes so everyone can use it. So I will update the current release in I don't know when it's done, but I think in the ballpark of some days, to actually enable everyone to just pull at least net flows out of Splunk and then use it for machine learning. So what it does is it takes the data, it cleans it, it prepares it, and then trains an HBOS model. And the interesting thing about it is it's already done. The training time of HBOS was 2 seconds. So this isn't a deep learning algorithm, it's a shallow, or it's a standard machine learning algorithm that tends to be extremely fast. And if you have a look, you might see that the true and false positive rates are horrible, which again is because of the fact that this data set really isn't representative of anything. So again, if you're interested in more details, come find me afterwards. I'd love to talk about it. I mean, the thing is, it's quite complicated because everyone has their own needs for, or even their own data, which also brings me to the fine print, because there are things I left out because they're really, really complex, which is explorative data analysis. So you're looking at your data set and looking at what it contains and how you could, how you could translate it into something that your machine learning algorithms understand. Because if you think of IP addresses, how do you try to describe your dog the difference between IPv4 and v6? You don't. That's going to be complicated. That's also the next point, the dataset preparation. So you're trying to transform it into exactly something that a machine learning algorithm can make use of. And if you collect much data, as in you're not only collecting net flows, you're also collecting application logs or, I don't know, web server logs. You could also think of feature selection, so kind of ignoring features that are not helping, but complicating the whole stuff. And last of all, there's normalization. So if you think of it, port numbers are a completely different format than file counts or connection counts. So you have to bring it all into the same ballpark to kind of support your algorithm. Again, deep learning algorithms in theory don't need it, but they also profit from it. So yeah, again, if you're interested, find me. And the thing is, what I want you to take out of this room today is think of what, ideally, before the next sales visit, think about what are you trying to do? What are you achieving? Is it classification? Is it regression? Or are you labeling your stuff? Or are you trying to predict a number? What data and features do you have? Because that dictates how you have to do preparation and what you can do with it. And then there is the, do you even real time? I mean, I told it already, deep learning stuff tends to be quite resource intensive, and at least the training part of it is not really suited for real-time applications. So maybe if you say, I don't care if my network gets hacked as long as someone is notified within the hour or week or month, depending on what you're doing, then it's fine. Go ahead and use deep learning. If you're saying, I want to get it now, maybe think twice about it, at least if you're constantly training your network. And there's the last point, which is high detection rates or low false positive rates. Currently, you have to choose one. I mean, there are still scientists trying to solve the problem of getting both. but it's still a choose one loss some weeks ago, and I'm still trying to actively mitigate, and I still have no end result in how I should do that. It's actually funny that you remind me of it, because I tend to try to forget about that.
You're welcome.
Thanks. But if you got an idea, I would be happy to talk about that with you. Not now, maybe later on if you want to.
Then maybe just one last question. So for your deep learning network, do you use like a special architecture that you came up with that like really fits the structure of this kind of data well?
I took the data, built an LSTM, and then tried to optimize or find the optimal parameters as well as the optimal count of nodes. So I tried to tailor the. So yes, I tried to tailor my network to fit. I tried to tailor my network to fit my data, and I think I'm doing a kind of okayish job. But I mean, time will tell.
Okay, I think we can take this discussion offline and continue it afterwards, because almost rest of the audience has already fallen asleep. So I think we may need a 5 minutes break right now, and we continue at 5 p.m. with our lightning talk session. Thanks, our speaker again.
Thank you.